Okay, questions on what we did yesterday? All right. So we started by looking at two agent, two goods economies, which can be represented in the good box. I spoke about how you can think of an agent, what is an agent in that framework. So consumption possibilities, what the agent enters the economy with, which would be endowments, preferences based on which the agent would take a decision. Competitive markets, we spoke about that, which technically define a budget set, and the agent chooses the best point in the budget. And then we spoke about what that means in terms of competitive equilibrium, graphical representation, and then I started developing the L-good model. And we stopped at the point at which we defined the demand set. Right? So we're going to go on from there. So, in terms of the figure that I drew, if you remember, I did say a few things about this yesterday. I will not always label the axes, but so that's the endowment of agent A. Prices define a budget set, and then I said the agent will maximize, and then I put in an indifference curve and said, well, you get a tangency, without really saying very much more than that. The key point is the agent is maximizing. Why do you get a tangency is what we want to look at now, under what conditions, right? So that we can use some calculus. So now we're going to assume that the utility function is differential. Hopefully you know what that means. Okay? So there's a definition of what it means for a function to be differentiable, and it has to do with limits, etc. That's what we assume. We needn't go into much greater detail than that. Now what we want to say is, how can we relate differentiability of U to the demand set? And we're going to do that in the following way. So there'll be two different parts to this. So the first one is what are called necessary conditions. So we're going to say if we have a point which is in the demand set for agent I at prices P, then there must exist, or there exists, a number which we denote by lambda for agent I. So lambda I is positive, such that what is true, such that, remember, if it's in the demand set, it's already in the budget set, that we already know. It has to be a point in the budget set which is maximal. So such that when you look at the derivative of the utility with respect to the L goods, we have L goods here, evaluated at your solution, which is X, then that derivative has to be proportional to the price vector. So for every good L, the derivative is the same multiple of the price. Okay? This is true for all of the goods in our set of goods. And what you spend is exactly equal to your endowment. In other words, we are looking, and there are some assumptions that are maintained assumptions. Okay, our maintained assumptions so far are that the utility function is at least weakly increasing. So you don't lose utility if you increase the consumption of input goods. Okay. So you will spend all your income, and in addition, this property that we sort of indicated yesterday is true. So I said your price vector is the normal vector to that line. In other words, the budget set is the set of all points at which the price vector is perpendicular to the points in the sense of when you take the dot product, you get a constant. And the gradient of the utility at the supposed maximizer points in the same direction as the price vector. So the two are proportions. So this condition can be stated in many different ways. You've probably seen it as marginal rate of substitution equals price ratio. Probably the way in which you've seen it. Okay, but we're looking at many goods here, so this is also true with just two goods. But this is the clearer way of understanding it. This is the first order necessary condition. Right. You can obtain this by writing out a Lagrangian, etc. That's a technique. The important thing about what the Lagrangian does is the result. And this combination is a result in one direction. So if it's a maximizing point, it has to be the case, provided the utility function is differentiable, it has to be the case that there is a number lambda I. Lambda I is positive here. We'll see why in a moment, but just to tell you, the interpretation is more income is better for you. You can raise the utility that you can generate by choosing your maximizing point. You can raise that utility if I give you more income. That's what lambda I positive expresses, and we'll prove that formally in a minute. Okay? But your first order conditions, the necessary conditions are, at the maximizing point, you spend everything. This has to do with the fact that we are working in a framework in which you will be on the budget line and not inside the budget set. And your marginal utilities are proportional to the price vector. Is that okay? Yeah? So these are necessary conditions. Very often, so when we do economics, we typically use one of these two. Which one you need to be careful with. Okay? So U is differentiable if U is also concave. I'm writing concave, but actually it's slightly weaker than that. It's quasi-concave, but let's write this concave. The result is still true. And if X in the budget set and for some lambda I positive. Okay, so suppose we can find a point in the budget set and we can find a number lambda I positive such that those two conditions hold. Okay, such that the first order conditions hold, then you found a maximizer. Such an X. Now, why am I doing this in some detail? The reason is, so far, we have a fairly simple setup where you can actually write this down and understand it very clearly. Once we start doing monetary economics, we'll be looking at the world in a much more complicated setup. You cannot do it in simplification. So it's important to understand the basic concept in simplification. Can I ask you not to take images, please? You need to take notes.
Okay.
Please. Thank you. And you have everything in the printed notes that you've been given. All the details are there. But as I said yesterday in class, it would be a very good idea for you to take notes in class, in addition to whatever you find in the printout. That's one way of making sure that the material is sinking in. Questions? Anything that you'd like to ask? So now, lambda I is called the Lagrange multiplier. Now, over here we have a single budget constraint, which is why we have a single multiplier. We will be facing problems in which there will be many budget constraints. And for each budget constraint, there will be a multiplier. Okay? So given that we are looking at a single multiplier, let's interpret it. Let's try and understand what it says. Okay. Interpretation. So I already said this. A couple of minutes back I said, lambda positive indicates that when I slacken your budget constraint, you're able to do better in terms of your optimization. Okay? You might have heard of this as lambda is the marginal utility of income. So we want to make sure that we understand exactly what it is in this specific demand problem. So some notation here. Instead of x, I'm going to write it as x tilde or twiddle. Okay, x twiddle. So if x twiddle solves our problem, then from our necessary condition over there, necessarily for some lambda twiddle positive, okay, I've dropped the I subscript because we're dealing with one person here. For some lambda tilde positive, the following is true. U and x tilde with respect to x1. So I'm going to do this interpretation when we have only two goods. In the notes, the notation is for the general case. Okay? But to write it on the board, I will do it with just two good case, which is good enough. So with respect to each good, when I take the derivative of the utility at my solution, that derivative is proportional to the price of that good, together with the budget constraint, which I'm going to write as P dot X tilde equals P dot O. Now the way to think about the problem is that my optimization depends not only on my utility, but it also depends on the prices that I face and the endowment that I have. So my solution will change if my prices and endowments change. Is it okay? Make sense? Yeah. It's called a parameterized problem. So if I were to shift my budget set because prices change, keeping the endowment the same, then I would get a rotation in the budget set. While if I were to change my endowment, keeping prices fixed, then I would get parallel shifts. And of course I could do the two together. Right? So now, we know that these conditions are true, and we're going to think of x tilde and lambda tilde are functions of, as I just said, p and omega. P and omega are the parameters of the problem. Please ask if something is not clear. Okay? Anything that you need as clarification. And you define the value of your problem. The word value will appear various times in this class, but over here it's the value of the problem. Okay? At prices P and omega, well, the natural thing to do is to say the value is the maximized utility at your solution. So x twiddle is the solution at prices P and omega. So the utility that you get at that x twiddle is your value. So it's the utility that is assigned to the indifference curve that passes through the solution point. Okay? Now let's take the derivative. Okay. So suppose I take the derivative with respect to one of the two endowments. Which one? Well, it doesn't really matter. So I'm going to call it d omega L. I have two goods. So I'm going to take the derivative of the value function with respect to omega L. So how do I do that? Well, u over here depends on xl, which is a vector of with two coordinates, x tilde 1 and x tilde 2. And then you have to use the chain rule. So you get d or partial u, same way as we've written there, x1. You have to be careful about where you're evaluating it. It's at your solution. You make it clear. I'm writing it out. And then you want to see how x tilde 1 varies with your variable. Omega does not appear directly over there. So I use the chain rule and I write it so. And similarly, I get partial u, partial x2 at my solution, which is a vector p omega. And then I get x tilde 2 omega 2. Is it okay? Yeah? But I know what each of these terms are. From my first order condition, I know that I can replace the first term in each of the products by the corresponding lambda tilde p1, and then I get partial x tilde, this is a partial omega L plus lambda tilde P2 partial x tilde partial x1. Again, omega L. Is that okay? Yeah.
Is the omega 2 on the equation just supposed to get one?
This should be an L. Thank you.
Yeah.
Okay? Now I also know that I'm satisfying the budget constraint. Okay, since I must always satisfy my budget constraint, I know that P x tilde equals P omega, and of course there are two coordinates here, and therefore I can write it, let's write it out, P1 x tilde 1 plus P2 x tilde 2 equals P1 omega 1 plus P2 omega 2. Now let's take the derivative. This is always true. So when I change my endowment of one of the goods by a little bit, any change that I see on the right hand side must be reflected somewhere on the left hand side, and the equality has to hold. That's just the budget constraint. It has to hold. Okay, so when I do that, let's write it out directly. I get 1 x tilde here is the endowment. It could be the endowment of good 1 or the endowment of good 2. Okay? So this is P1 plus P2 partial x tilde 2 partial the same variable, omega L. And that will be equal to P1 partial omega 1 partial omega L plus P2 partial omega 2 partial omega L. Now, from this side, it's clear that omega L is either omega 1 or omega 2. Okay? My endowment of either apples or bananas is changing. One of them. And I know which one. So the one that's changing will have value 1, and the one that's not changing will have value 0. Do you agree? right? So this is a long way of saying that my income will change by the price of the good whose endowment is. So I increase your endowment of apples by 1 unit, your income will change by the price of apples. Is it okay? Clear? Sometimes many of these things are very obvious when I say them repeatedly. The reason is I want to make sure that you can understand what the argument is. So now we are almost done. Because all of this is equal to PL. But all of that is what appears here. Okay? So, lambda tilde, this seemingly strange number, has a very clear interpretation. All right. Sort of falls into place now. So the Lagrange multiplier is exactly equal to 1 over the price times the change in my maximized utility when the endowment of the good changes by 1 unit. You can also think of it as what happens if my income changes by 1 unit. My income changes by 1 unit. That's as good as saying, given the price, my endowment changes by 1 over the price. Price times quantity will be equal to the value. If the income is to change by 1 unit, that's exactly by how much the endowment needs to change. And that gives me the interpretation. Is it okay? Now, I'm not going to ask you to derive this, but I can ask you to use it in a manner which might not be obvious to you. It's important you understand. I mean, why are we doing this? But again, once we start doing monetary economics properly, we will be in a framework where I will not be able to show these computations on the board. We will work directly with Lagrange multipliers. So it's important to understand what is a Lagrange multiplier, which is why we're doing this here. Not just telling you that this is it and you need to believe. Hopefully you do believe in because you see a proof. That's what's going to be different in this class in many ways. You will actually see things being done on the board and in things. Okay? Questions? Anything that's not clear? Anything that you'd like me to go over again? Okay. So with that done, we can start talking about, so I'm going to, I'd asked yesterday, and presumably I can do the same thing today, which is I can erase things and write on the same board. If you would prefer me to leave it on the board, I can move the boards. But if it's all right to erase it, that's what I'm going to do. Okay. So now we want to put in a few more definitions. It's a bit of a so formally, we need to talk about what are the things that we're talking about. So feasible allocation. Fundamental notion in economics. Okay, specific problem. You can say you have a cake and you want to divide it across a certain number of people. So then you need to define feasibility in terms of those people and the cake. Allocation. Sorry. In an economy, E is going to be given by what? It's a list of vectors. And for each agent, you have a list of how much they are consuming on each of the goods. So you have L goods here. So for each agent, you have an L-dimensional vector. Okay? Where such that you want to make sure that for each agent, Xi is consumption feasible. So it's an RL plus, which is the consumption set.
Sorry to interrupt, but I think I dropped something on the war.
Yes, please check.
In my previous seminar. It's a little black case. Okay. Sorry about that.
No, that's all right. Okay. For each agent. And in addition, it better be the case that what we're allocating across everyone put together is no more than what you have to distribute. Sum over I in script I of xi is no more than the sum over I of omega. That's a feasible allocation. So feasible at the level of the individual and at the aggregate level. Okay? Please ask if something is not clear. Now you might wonder, why haven't I called this market clearing? Well, in that definition there are no markets. We have to bring in markets before we can talk about market clearing, which we will. We've already spoken about prices, so we can talk about markets because we have them in the background. Okay? A competitive equilibrium for the economy E will be what? It's a list, this time, of consumption vectors x star 1 to x star I and prices, such that 1, the consumption part is a feasible allocation. Allocation for the economy E. So that's one part. It's market clearing with an inequality. The important thing is you're not spending more than you have. And of course, you want to make sure that for each agent, what that person is being assigned is in their budget set. Is in their demand set, not necessarily in the budget set. So, utility maximization subject to a budget constraint is taken care of for every agent, and in addition, it's a feasible allocation. Is that okay? Questions? Anything that's not clear? Again, this is not about memorizing these things because you put them down in an essay. I'm not going to ask you to write an essay on the comparative equilibrium. That's not what you're required to do. It's so that you get used to a certain way of thinking about things, being careful about how you write things, what is it that you mean, everything has to be clarified. Because otherwise, it's going to lead to a lot of confusion. Hopefully this will not be particularly confusing. Okay? So in a competitive equilibrium, as we've described before, every agent maximizes given prices, okay, and their choices are compatible in the aggregate. They're feasible. Okay? Now, a fundamental definition, which I've referred to yesterday, without really telling you what it was. And I don't know whether you've seen this before, because you seem to have not seen many different things, but it's important to make sure we understand what we have. So a lot of what we will be doing will have to do with how well our resources are being allocated. And our test for that will be Pareto optimality. So efficiency, inefficiency, etc. The benchmark is always a notion of Pareto optimality. Okay, so Pareto optimality, as I explained yesterday, was you look at the people in this room, okay, myself out of it, I'm looking at how things are assigned. So there's 7 people here. You all have your things with you. You're not allowed to leave. Everything stays here. And you ask whether there is a way to reassign your goods, given what you currently have, so that nobody is worse off, at least one person is strictly better. If you can do that, you found a Pareto improvement. This is the first thing you need to be clear about. What is a Pareto improvement? So Pareto improvement is a feasible reallocation of resources such that everybody is at least as well off and at least one person is strictly better. That's a Pareto improvement. And you say an allocation is Pareto optimal if you cannot find Pareto improvement. It's a convoluted definition, but it's a fundamental concept in economics, and therefore we need to define it carefully. So a feasible allocation for E, the notation that we use is the bar, x power 1, x power I, is Pareto optimal or Pareto optimal allocation if there is no Pareto improvement, which I'm going to write as there is no feasible, no other. These things can be written in many different ways. No other feasible allocation for the same economy. So the economy specifies resources and preferences. In this case, it's feasibility, it's just resources. So if there is no other feasible allocation denoted, so we need the notation here, so I will be using x tilde 1 to x tilde I, such that what is true? For every agent utility, since we're looking at economies where you can always work with the utility function rather than preferences, that agent receives from the alternative is at least as good as what they received in the status quo, and for some agent I bar J, U, it's a bit of a mess to write, for that person, and therefore that person's allocation is strictly larger than what that person was receiving in terms of utility at the original allocation. So there is no Pareto improvement. That's when the allocation is resolved. Is that okay? I will not be repeating this definition when we go to more complicated economies, because it becomes messy to write with. The main complication will be we will be looking at economies in which the time horizon extends forever, and or there are an infinite number of people with the generational overlap. That's messy. So long as you're clear about what it's saying, you'll be fine. This is why the definition is there. Questions? Anything you want to ask? You're probably wondering this, there's nothing about money. Nothing. Absolutely nothing. There is nothing about money so far. And there won't be anything regarding money for at least another 2 or 3 lectures. Because we need to build up the basics. Okay? Now, what I want to do next is speak about how all this works. Why are we using, definitions are all fine, but we probably want to do a little more and have a result. So that's what we want to get to now. So I'm going to start on this side of the board and then I'll move to the other. So what I want to do now is speak about this invisible hand of the market. It's all sorts of things. Adam Smith, anytime you watch something on television or you read about economics, when things are going well, they'll just leave the market alone. Why? Things are perfect. You don't need to do anything. And then all of a sudden, people start screaming, and the government needs to, the central bank needs to intervene, and you have Trump saying that he's going to fire the chair of the Fed because interest rates should be lowered. Why? Why all of a sudden, all these people who are essentially the masters of the universe in capitalism suddenly start thinking that things are going wrong? Okay? And the answer is they're not going to be able to tell you. They have no clue as to what they're wrong. We will hopefully be able to say a few things. So what I want to convince you about is that it's remarkably simple to come to the conditions under which such a statement is true. Which statement? That a competitive equilibrium is played out. Okay? The mistake is in not understanding what makes it true. That's where the mistake is. So first, we will understand in the simple framework, and it is very simple, exactly why it's true. We'll do a proof. Hopefully we'll have enough time today. Okay? And from there, we will understand how things need to change, essentially, so that you reflect reality, and you will see immediately that that result will no longer be true. And that's where things like money will come. All right? So we want to speak about the first welfare theory, which you may or may not have heard about, but it doesn't really matter. You have enough on the board to be able to at least state it, and in a moment, we will also have the condition that you need for it to be true. So the condition that we need is the following key condition. So this is what I'm going to start with. The idea is that you take a consumer, any consumer, and you're going to say that, look, given the bundle that the consumer is considering, it has to be the case, this is our assumption, that if I restrict the consumer to choose bundles that are nearby, and nearby could be as nearby as you want, regardless of how much you restrict the consumer's movement from the bundle that the consumer is currently at, there is a bundle, at least one, which will make the consumer strictly better off. Is that okay? That's the notion that we need. It's called local non-cessation. Local non-cessation, which is actually satisfied in the economies that we are looking at, because we've assumed that the utility function is strictly increasing. So now we're going to move backwards in some ways. We're going to allow for much more general frameworks, where all that you need is local non-cessation. So, as I said, local non-cessation says, consider a bundle for consumption, regardless of how close you want to be to that bundle, and I'll specify what that means. You can find another bundle which that consumer strictly prefers. It's never the case that the consumer says, I don't want any more. If you give the consumer a little more resources, the consumer always says, yes, I'd like it. Is that okay? So what we will be doing essentially is ensuring that each consumer spends their entire income. It's one part of it. And the other is that their utility maximizing point is also the least costly way of getting to that utility. It's called cost minimization. That's the key idea here. Yeah. So local non-cessation says for any consumption vector x in RL plus and a positive number epsilon, there is a vector y, which is also in the consumption set, so which is RL plus for us, such that the distance between x and y, and the distance here is the Euclidean distance between vectors. So you take the square of the components, add them up, and take the square root. So the distance between x and y is less than epsilon, and the utility that you get from y is strictly larger than the utility that you get from x. That's local non-cessation. Is that okay? Repeat. Pick a point, regardless of how close I want you to be to that point, that's the epsilon. You have to be within epsilon of x. I can find an alternative y which is strictly better. Okay? I haven't asked you whether you've seen the first welfare theorem or whether you've seen a proof, because I might get different answers and I don't know what you're going to get. Okay? But we're going to prove the theorem. I still haven't told you what the theorem is. The theorem is, if you look at a competitive equilibrium of an economy in which every agent's utility satisfies or preferences satisfy local non-cessation, then every competitive equilibrium of such an economy is Pareto optimal. Lots of words. Competitive equilibrium are Pareto optimal, invisible hand. If you want to call it that, that's fine. Okay? So that's the theorem. Now, this formal statement of the theorem I should write on the board, so let me do that. As I said, informally it says if preferences are locally non-satiated, so that no individual is ever in a situation where they can maintain their utility by spending less, then the allocation of commodities in every competitive equilibrium is Pareto optimal. The idea of the proof I'll come to in a moment, so let me just write the formal statement. Okay. So this is one of the most, possibly the most important result in general equilibrium. General equilibrium has a bunch of results. One is, what is a competitive equilibrium? When does it exist? Something that we haven't spoken about at all. Once you have existence, you want to ask, what are the efficiency properties? That's the first welfare theorem. And yesterday I mentioned the second welfare theorem, which, if I have time, I'll speak about a little more today. Or repeat. So let x1 star, xi star, p star be a competitive equilibrium of the economy E, and suppose local non-satiation holds. The proper statement is in the notes. Okay? If you ever have to say anything about this on an exam, you should write everything out properly. It's just more difficult on the board. For each agent I, then the allocation is Pareto. Okay, that's the first one. The only difference with what you might have seen before is you're putting in a specific condition. We want to do a proof. We want to make sure that we get the result and that we are not assuming more than we need. Is that okay? All well? Okay. Since you have all of these things in the notes and written, so what would be the approach? So we will start by saying, suppose you can find an alternative. That's a Pareto improvement. So suppose there is an alternative that is a Pareto improvement. The first thing is, being a Pareto improvement, it would be the case that at least one person is strictly better off nobody's worse. Okay? And from there we proceed by saying, under local non-satiation, that everybody who's at least as well off will be spending at least as much. That's going to be the difficult part. And the person who's strictly better off must be spending strictly more. Because otherwise, from our definition of the demand set, right, the demand set, the definition was that there is nothing in your budget set which gives you higher utility. That's what we said. That was the demand set. We said, if there is a point at which you get strictly higher utility, then that point costs more than you have. So for the person who's strictly better off, that person is clearly spending strictly more. For everybody else, we need to prove that they cannot achieve that level of utility by spending strictly less. If we do that, then the supposed Pareto improvement will cost strictly more than your current allocation. And then we will show that that necessarily means that you must be allocating more of some good than you have. Must be feasible. Okay, those are the lines of proof. So let's see how much of it we managed to do in the couple of minutes we have, and we continue tomorrow. I'd hope to do more, but I'm being slowed down by, now I'm used to writing on whiteboards. takes me longer to write on a green board or a slate board. But let's see what we do. Okay? So, suppose this is the tricky part. Let's see how much of that we managed to do. So X star is the demand point for agent I. Okay? Can I find, or is there Y such that I's utility from Y is no lower than I's utility from X star, and I can buy Y for strictly less than what I is paying to buy X star. So I don't know what you have in the notes. I've written it as X star I. Okay? So if you could find such an alternative, then that agent would be able to buy a bundle which is just as good. So from the utility perspective, it's no worse, and yet spending less. That's what we're checking here. And the claim is that under local non-association, this will not happen. Okay? So suppose yes. Suppose yes. By local non-association, which I'm going to write as N and S, there is, so close to Y there will be a Z. There is Z such that, so this is the part that says Z is very close to Y. What you spend on Z is very close to what you spend on Y, plus the difference between what you spend on Xi and what you spend on Y. And the utility that you get from Z is strictly larger than the utility that you get from Y. Remember, local non-association, the key point is that you, even if you're very close to Y, very close being specified in that way, you can still do strictly better. Regardless of how close I want you to be to Y. And over here I'm specifying as to how close in terms of how much you spend. And I can do that. Okay? But then, as you notice, Z is strictly better than Y. Y is at least as good as X. But from here it's clear that term cancels out with that one. You could have afforded to buy Z in terms of what you were spending at Xi star. Okay? Implies that Z is in the budget set, that's from 1, and the utility that I gets from Z is strictly larger than the utility that I gets from Xi star. Hence, it could not have been that Xi star was in the demand set. I found a point at which I can afford to buy that vector of goods, and I do strictly better than my supposed maximizer. So that would not have been my maximum. Once again, you will not be required to produce this proof on the exam. None of these proofs are required. Once we start getting the material for the exam, I can take. It's just so that you understand what is happening. Now this is likely to be confusing. And we're just about over on time, so time is 55 minutes. So please ask.